Okay, last chapter. Kind of interesting. Of course, all of it is. How do you pick a favorite chapter? It's just so hard. The last one, by virtue of the fact that it's the last one, that's why it's your favorite. Okay. We're going to end with acids and bases. It's very, very important biologically. You're going to test for this whether you're in MLT, whether you're in nursing, whether you're in respiratory care. It doesn't matter. This is very important in terms of health. Okay. So I'm not going to be able to put a lot of health twist on it because this is general theory chemistry, so I can't focus it on health. But it'll give you a better understanding of what this means. What is it actually that you're doing when you measure the pH of something? What does it mean? Why is it dangerous? Why is it useful? What are acids? What are bases? We interact with them daily, all the time. Okay? So here's some common products. You'll see that here's some common acids. I'll talk about all what acids are and that kind of thing. A lot of fruits are going to have some natural acids in them. We know that. You drink enough orange juice, it can hurt, right? Lemons, all that kind of stuff. So a lot of your heavy-duty cleaning agents and toilet decloggers and etc. Are some of your strong bases. Drano is sodium hydroxide. We'll look at some more of that later. Ammonia, oven cleaner is extremely basic. So we'll examine the properties of some of these things. But this is common. You open up your cleaning cabinet at home, you're going to find some of this stuff. You're going to find bases. You're going to find probably more acids in your food pantry than anywhere else, if not out in your barn, if you have any like muriatic acid or use any cleaning agents outside, like on concrete or anything like that. You can certainly, with acids and bases, there's plenty of reactions right at home that you could mix and make. You guys know the Works bomb, right? A little Drano, a little aluminum foil. I'll talk about that a little bit later. I'll show you the reaction that makes this happen. Usually metals don't react and evolve a gas when you mix them with bases like that, but aluminum is a rare instance, which makes it handy because it's cheap and makes for a good bomb. All right. First of all, we got to revisit electrolytes. Now we know, I mentioned this already, an electrolyte is going to be something that can dissolve entirely. Its pieces will fall apart into solution, and it is going to be ions that are floating in solution. And they have the ability to distribute electrical charge. They can move electrons around. That's what an electrolytic solution does. Okay, so your salts are going to be electrolytes that are soluble in water, like your sodium chloride is a salt, your sodium nitrate, all these things that are salts. They are ionic compounds that dissolve in water. And they are all very strong electrolytes. We're going to judge the strength of our electrolytes on how well it dissolves. If it dissolves very well and all the pieces fall apart, then it's a really strong electrolyte. If some of the pieces fall apart, but some of the molecules stay together, then it's going to be a weak electrolyte. If none of it falls apart and all of it stays together, it is a non-electrolyte. Okay? I mentioned this a little bit before. All right, so what makes acids acids? The most important element associated with acids, as you already know because we memorized a bunch of them and learned how to name them, is hydrogen. Okay? Hydrogen is what makes something acidic because hydrogen is the tiniest atom, and as it is dislodged and as it goes somewhere, it likes to react with things, and that makes it of chemical significance. All right, so acids are going to form, if acids are dissolved in a water solution, they're going to form free-floating hydrogen ions in that solution that are going to be of interest to us. So why are bases studied alongside with acids? Acids. Not so much with the first. Just like a runner, and I don't even know how that happened. Just like in softball, baseball, whatever, you have a base that accepts a runner. You're going to have a situation with a base that can actually accept the hydrogen. It'll react with hydrogen. It will combine with hydrogen, and you've heard of neutralization, right? We talked about neutralization reactions. What bases will do is combine with hydrogen ions in these water solutions. All right. Another thing, though, that they will do that you can witness is not just combining with hydrogen, or sorry, just sucking hydrogens out of solutions, but they actually can put hydroxide ions into solution. Okay, so your really strong bases are going to be like your sodium hydroxide, lithium hydroxide, things like that. This will all, I'm just introing here, we're going to talk about all of this. Okay, so it may either, that means that a base could either, if you drop it in solution, it may fall apart and release a hydroxide ion, or it may react with water and yank an OH from water and leave behind an H. Okay, if it yanks off an OH, then it's going to put those hydroxide ions in solution. And if it's going to leave, if it just depends. I'll show you what I mean a little bit later. All right. So how did acids get their name? Anybody need to enunciate? I have a poor enunciation problem. So, yeah, that's what I get from backwoods Indiana. Anybody speak German? No German speakers in here? The German word for acid is sour, like sauerkraut. Acids, well, it is. That's how it's made. I mean, it's made from acid secretions from microorganisms. That's how you make that stuff. They taste very sour. Lemons are very acidic. Bite into one. They are named sour because of that. But what they do, some characteristics about them, they have a sour taste. They react with metals. Okay, we know that they can dissolve metals a lot of times. So you take a piece of zinc, you take a piece of magnesium, drop it in hydrochloric acid, it'll dissolve. It'll just separate out into its ions. Like in this case here, if I take a piece of aluminum, drop it in hydrochloric acid, look what's going to happen. I'm going to get aluminum chloride, which will be an aqueous salt that will stay dissolved. I don't have that aqueous labeled up there, but that's what it would be. And you would have hydrogen gas evolved from that, and it would all bubble and fizz. When you drop metal in acid, you'll see that, and usually always that bubbling and fizzing is going to be associated with hydrogen release for when this falls apart. Okay, because think about what is happening. Hydrochloric acid means that you've got a solution that's mostly water, and suspended in that water is a whole bunch of hydrogen ions and chloride ions that are all floating around. That's a hydrochloric acid solution. So when I drop in aluminum, what happens is the aluminum sticks onto the chloride. Well, they don't really stick together. They form a solution. The aluminum and the chloride gravitate towards one another. And what will happen is now the hydrogen is sort of left out of the loop. And if the hydrogen is left out of the loop, hydrogen is a diatomic molecule. If you remember, the diatomic molecules, if there's nothing for them to react with, they will react with themselves, and they will form a gas. And then that's what will happen here, and then it'll come back up out of the solution. So you see this effervescence that you can see there. Corrosive. Corrosive means it's able to take, like metals, for example, and put them into a solution. If you want to clean something, clean rust off something, realize that rust is a metal hydroxide compound. Okay? If you want to put some muriatic acid, which is hydrochloric acid, you can buy it at Lowe's. Dump some on there. It'll be corrosive. It'll eat away. In other words, put into solution those atoms. If it reacts with a carbonate, hydrochloric acid can react with calcium carbonate to give you, think about it, switch places. This guy and this guy is going to come together. Calcium chloride is the salt. And then what will actually happen is, think back to gas evolution reactions when we talked about those. If you see CO3 and it falls apart, there's a gas held within that, a very common gas. It's CO2. So what will end up happening is one of those O's is going to fall off, hook onto these two hydrogens to form that water, and then you're left with CO2 by itself, and that's where that CO2 comes from. So acids will react with carbonates. They will react with metals to dissolve them. So they can also take litmus paper and change the color. You guys have heard of it, like someone saying a litmus test before. Litmus is one way to say whether or not something is acidic or basic. Are there free hydrogens present, or are there not? Are there free hydroxides present? Anyways, you can change the color of dyes with them. You can use litmus paper to test. In this case, blue litmus paper will turn red in the presence of an acid, in presence of excess hydrogen ions. Okay, and then what will happen is, and I'll show you why here in a second, but another fundamental rule of chemistry is that as acid reacting with the base will give you the same two things every time. Acid plus base yields salt and water. Okay? Acid plus base will give you salt and water, and I'll show you that in a little bit.